The last tutorial we looked at what word embeddings are. In this tutorial we are going to look at how word embeddings are calculated. They're calculated using two techniques. One is supervised learning, the other one is self-supervised learning such as word2vec or globe. In this video we are going to look at supervised learning technique for word embeddings. In the future video we will cover word2vec and globe, and today's video will go over some theory on how supervised learning works for word embedding, and then we'll write some Python code as well. In last session, we saw how you can represent words using the vectors like this, where it can represent the meaning of word meaningfully. For example, here I have two cricket players, Dhoni and Cummins, and one of the ways to represent the word vector is by using the features such as person, healthy, fit, location, and so on. And when you do that, what you find is the vectors for Dhoni and Cummins, who are cricket players, they look quite similar. You see like 1, 1, 0.9, 0.87, and so on. Whereas the vector for Australia, which is a country, looks quite different. And you can have number of features that you can use for word embeddings, so that when you're comparing Cummins and Dhoni, which are cricket players, their vectors look same. And when you're comparing the teams, Australia and Zimbabwe, their vectors also kind of look same. Now the question is, how do you come up with these features? It seems very laborsome task. The good thing is neural networks can compute these features for you. These are not handcrafted. They are derived while training your neural network. And there are two techniques which I already talked about initially, which is supervised learning and self-supervised. So word2vec and glow are the self-supervised learning techniques. In this video, we are talking about supervised learning technique. What happens in this technique is you take a NLP problem and then you try to solve that NLP problem, and as a side effect you get word embedding. Now the term side effect is very important and you will see why. Let's say you are doing a food review classification, whether the review of the food is positive or negative. This is a typical NLP task. Now in order to do this food review classification, you have to train your neural network, and after the neural network is trained, you will get word embeddings as a side effect. So the problem that you're solving here for food review classification is almost like a fake problem. You don't care about this problem very much. You care more about the word embeddings. Now you have, let's say, 100 food reviews. For that, what you will do is you will first decide the vocabulary. So vocabulary is all the words that appear in the food review. So let's say you have 5,000 words in your vocabulary. Your goal is to come up with this word embedding vector with dimension 4. It could be dimension 10, dimension 300 is very common. So this is something like trial and error. Let's say for my problem, I'm saying I want a word vector which is of dimension 4. And these numbers will be calculated in such a way that similar word will have similar type of vectors. So eventually your goal is to come up with this 4 by 5000 embedding matrix, also known as E. So the first thing you need to do is you need to come up with a one hot encoded vector. You all know about one hot encoding already, where for the after, this row is the one hot encoded vector, where there is 1 here and remaining numbers are 0. Similarly for food, 1 is here and remaining numbers are 0. So now you start training your neural network. So what you do is you take your first training sample, just to keep this thing simple. I'm saying my review is only 2 words, nice food. Actually it will be long, like 20, 30, 40 words. Then you come up with a random weights in your embedding matrix. See, this embedding matrix is that 4 by 5000. Okay, let me show you. It is this matrix, okay? Don't confuse it with this one hot encoded vector. So it is this matrix. So you want to compute this matrix. So initially you will come up with some random weights. Let's say these are the weights 0.5, 0.2, 0.3. These are randomly initialized at the beginning. Now you take one hot encoded vector for word nice. So you see nice is a third word, so 001, and you multiply it with the embedding matrix. If you know about matrix multiplication, what will happen as a result is you will get this particular column, because to multiply matrix you take the first row, you multiply it with the column, and the column has 1 in the third column, so third column is 1, so you get 0.9 here because remaining numbers are going to be 0. You do the same thing for the second row, this second row, multiply it with here, the third element has 1, so third element is 1 2 3.2, so you get 0.2 here. If you don't know much about matrix multiplication, I advise you refresh your concepts. Then you flatten the vector. So I have two word embedded vectors. Now these are not perfect. Neural network is still training, okay? So these are two individual word vectors for nice and food. You flatten them, so you get like 8-dimension vector. Then you feed it to sigmoid function. It's like a single neuron sigmoid function, which will give you y hat, which is y predicted. You compare it with your y truth. So nice food is positive review, correct? So you compare y hat with your positive review, which is 1. Then you get loss and you back propagate that loss. Now when you back propagate that loss using gradient descent, these weights will update. See, right now it's 0.9, 0.2 and so on. See, the weights are updated. You see, it was 0.9, 0.2, now 2.3, 1.6. I have put random numbers, friends, but you get the point. So in this pursuit, your matrix, embedded matrix, will keep on changing. Then you take the second training sample, poor quality food. This review is of course negative. So you repeat the same process, flatten out the vector, compare it with how I had, do back propagation, and you again change these weights. So this time you will be changing the weights for poor quality food, like these 2-3 columns. Now you will ask me a question, which is, in the first sample we had only 2 words, the second sample we have 3 words. So the neural network architecture needs to be fixed. It cannot change, right? In the previous one I had only 8 neurons in my first layer. Here I have 12 neurons. How is that possible? Well, you take the maximum sentence size and you do padding for the remaining words. So let's say my maximum sentence size is 3. When I have nice food, the third word I will say padding. Padding means all zeros, so all zeros you get, all zeros. So that way my neural network architecture doesn't change. The first layer has fixed number of neurons, which is equal to the word embeddings of the maximum length sentence. And you feed all your samples, let's say 10,000 samples, you keep on feeding it, neural network keep on training. Eventually it will come up with a matrix, embedding matrix that can represent words nicely. So if you look at this particular example, nice and good are kind of similar words, so the numbers are kind of similar. You see 0.4, 0.38, 8.1, 8.2. So when you compare these two vectors, it will say, yeah, these two words are similar. Similarly, poor and weak are similar, so it will compute the vectors in a way that those numbers are matched, and if you look at the cosine similarity between these two vectors, it will be close. Basically, cosine similarity of 1 means the vectors are close, so it will be like that. So this is the quick theory behind supervised learning approach for embedding metrics. This approach is not very popular nowadays. The more popular approach is word to vec, but I still wanted to show you how this particular method works, and will now write Python code for this problem. Before we begin, I want to say thanks to Jason Brownlee for his excellent article. I'm going to provide the link in the video description below. The article mentions the word embeddings in a nice way, and some of the code I have written is based on this awesome article. The website Machine Learning Master is awesome. He writes so many good articles, so please check it out. Here I have imported the important libraries in Keras and NumPy, and then I'm going to do the food review classification. I have like 10 reviews here, very simple data set, and then 10 labels. So the first 5 are positive reviews, you can figure it out, and the next 5 are negative reviews. So the first thing we're going to do here is, we will convert that into a one hot vector. So there is a method called one hot, and what that method will do is it takes the review and then you specify your vocabulary size. So let's say if you say 30, it will give a unique numbers, so amazing, it gave 5 number, restaurant it gave 16. So the number will be between 1 to 30. If I say 500, the number will be, the max number will be 500 basically, you see, 256, 39. So this is the vocabulary size, this is the review. Okay, so one hot encoding, again, it's giving the fixed number, unique number, and internally Keras, the layer will convert it to 0011 and so on. Okay, so that's number one thing. Now what you want to do is you want to, let's say, initialize vocabulary size. Let's say my vocab size is 30 and I want to encode all these reviews. So see how I did amazing restaurant 516. So similarly, all the reviews, I just want to convert them into one hot encode or encoded vector. So if I write this code, it's a simple list comprehension. I went through all the reviews here. For each review, I created encoded vector. So you will now get this encoded reviews. You can see. Now we saw in our presentation, if you remember our presentation, let me pull that up, that we need padding. So we need a maximum sentence size and we need to pad, okay, the sentence, because see, some sentences are 3-word long, some are 2. So the 2-word sentences we need to do padding and we need to append 0. So let's say my max length is 4, okay, or maybe I can make it 3 as well. Okay, and then I will do this. So there is a method called pad sequences in TensorFlow Keras. So I'm supplying all encoded reviews into pad sequences. I'm saying my maximum length is 4. Padding post means pad the reviews towards the end. So now see, towards the end I get zeros. Okay, I can do 3 as well, actually 3 makes more sense. Okay, so now my padded reviews have a equal size, right? Every vector size is 3. Now the next step would be embedded vector size. Let's say I want my embedding vector size to be 5. Like here I had it 4, like 1 2 3 4. Here I had 4. In my code, let's say I want to do 5. All right, so I did 5. Then I need to create my model. So my model is what, like sequential. Okay, and then I need to add my first layer. So my first layer, if you again look at this particular diagram, my first layer will be embedding layer. Okay, this particular layer. Okay, so embedding layer, for that I have already imported embedding class. And the way embedding class works is it takes a couple of arguments. Okay, so what is the first argument? The first argument is vocab size. Then the second argument is the vector size. So vocabulary size is 30. You see 30 here. Then my vector size. After the vector size, you will supply the length. So max length is 3. And I need to give it a name so that I can use it later. Okay, and then my second layer is, okay, what is the second layer? Again, if you look at the diagram, once you get embedding vectors, these vectors from your embedding layer, you want to flatten them. You want to flatten them to create this particular vector. So I will just say flatten. And the layer after that is one neuron sigmoid activation function. So it will be a dense layer with a sigmoid activation. Okay, and then I will execute that. Now just to make it more convenient, my X is padded reviews and Y is sentiment, correct? This is my X training samples and this is my labels Y. So just to make it easy, I'm just putting them in a different variable called X and Y. And I will now compile my model. Now usually we end up using Adam as an optimizer and binary cross entropy because the output is either 1 or 0, right? Like the review is positive or negative. That's why binary cross entropy. And then you can print the model summary. And my model looks something like this. See, embedding, my embedding vector size is 5. In this particular example here, I had like 4. I can make it 4 actually, just so that it matches my presentation. So 4 here, and when you run it, see the embedding vector size is 4, the max sentence length is 3. All right, once you do flatten, you will get 12. Why 12? Well, see, 4 4 4, so 12. So this will be a 12 vector size, and then there is just one neuron which is dense. And now you are ready to train. So you supply your X and Y, epochs 50, you train your model. So my model is trained. I got an error, by the way, initially because I had another notebook running which was using my GPU, so I had to kill that. Once the model is trained, you evaluate the accuracy. Accuracy is 1. It's a small data set, friends, so it's expected the accuracy is 1. Now what you do is, see, I mentioned earlier, the sentiment classification is a fake problem. I'm more interested in word embeddings. So while solving a sentiment classification problem, I also got my word embeddings. And word embeddings are nothing but those parameters in your neural network. And you already know, when you have a neural network layer, you can use this method. So you can say model.getLayer embedding. So this is the name we gave here. Now you realize why we gave that name. You can call this method call get weights, and that will give you all the weights. See, these were the weights I was looking for, like 4 embedding. See, 1 2 3 4. So that 4 embedding vector is nothing but this 1 2 3 4. Okay, all right. So the length, okay, let me just store this into this and see what is my length. Well, length is 30 because my vocabulary size was 30. So now if you want to look at word embedding for, let's say, food nice. So nice is 29. Okay. I mean, somehow it gave 29 for nice and food both. If I had increased the word embedding to, let's say, 50 maybe, it would have given a different so you see it gave a different kind of embeddings. So here I'll probably run that. Okay, and the weights are 50 basically. And if you look at the word embedding for nice, the number that we got for nice was 11 and food was 1. So the word embedding vectors for nice, see, nice is 11 and amazing is 3. So let's look at 11 and 3. Okay, so I will look at 11 and 3. So weights 11 and weights 3. So 11 and 3. Okay, what is 11 and 3? So 11 is nice and 3 is amazing. Now these two numbers are not, these vectors are not same. Actually, you know, nice and amazing are kind of similar words. So you would you would think these numbers should be same, but our data set was very small. Okay, if you run it on a huge data set, maybe you will find this vector to be similar, and you can compute the cosine similarity of these two vectors. But at least this coding session gave you an idea on how Keras embedding layer works. Many times people have a question, how Keras embedding layer works. So the way Keras embedding layer works is during the process of solving the NLP task, it will compute the embeddings on fly. Now the other way of computing embeddings is you can save this. Like usually what people do is they compute this, they save it to a file. And later on when you want to perform a different type of task, you can load saved embeddings from that file into this layer. Okay, and that's what this awesome article goes through. It talks about loading the embedding vectors from file as well. So it has a section number 2, pre-train and glow embeddings. So I'm not going to cover all of that. Hope this video give you some understanding. I would highly suggest that you also try this code out, maybe try it out on a bigger data set and see how it goes. Thank you very much for watching, and I will see you in the next tutorial.